Okay, so just open your books to wherever this page was. Okay, so beginning with where we left off, we had this object rolling downhill, and we said some of the forces in the x direction equal to ma, so that gave us mg sine theta minus fs equal to macm, right? Newton's second law. Some of the torques equal to I alpha, and the only torque exerting it. Please pay attention here, guys. This is the key in this equation is the cm. We're taking things to be measuring things about the center of mass. So the torque is taken about the center of mass of the object, and the center of mass is right here. And the forces that exert a torque about the center of mass are, well, not n, because it points straight into the center of mass, and not mg cos theta or mg sin theta, because they emerge from the center of mass. The only force that exerts a torque is the force of friction. F times R is the torque, is equal to ICM alpha. Fine, good. We don't know F, don't know A, don't know alpha. Three equations, two unknowns. The third equation is ACM equal to alpha R. Put them all together, and we came up with a result that ACM is equal to 2/3 G sine theta. Hey guys? So, and the force of static friction was 1/3 of mg sine theta. Something important to note is that this result will depend on the moment of inertia of the object. This will not be the same for a sphere as it is for a cylinder, as it is for a ring. And the force of friction will also be different on these objects. It's not always going to be equal to, or seldom is it going to be equal to mg cos theta mu k, or and mu k mu s, whatever. You know, if we're dealing with static friction, it's mu s. It's kinetic, it's mu k. In this case, it has to be, unless it's skidding, is going to be static friction, but it's not equal to n times mu, or mu s. All right. The new thing now, guys, that we're about to do is that rolling motion can be considered to be, please pay attention here. Close your laptops, please, again. Laptops, close. Tito, close them back. So guys, the thing to pay attention to, guys in the back, please close your laptops if you're not using them for the course. Thank you. We note here that in this approach, rolling motion is considered to be a combo of what? One is translation of the center of mass. This massive object is moving. Part of the kinetic energy is there. Another part of the kinetic energy goes into, on top of this motion, causing the object to what? Rotate about the center of mass. And this is summarized by some torques about center of mass. Please pay attention now. Okay. Another way to look at rolling motion is to consider it as a set of successive rotations about one point, all of it. What am I talking about? Where is the point where the speed is 0? The point on the wheel in contact with the surface, its speed is 0, right of the surface. What does that mean? When that point on your tire gets in touch with the ground, its speed will be, for that brief moment, 0. Why? Because if it's not 0, then you're skidding or spinning. You wouldn't want either. If you might want that, but typically it's not what happens. In ideal rolling, the speed at that point is 0. Okay. This means that that point can be considered as what? Kevin, you schmuck. Stationary is the same as not moving. Immobile? What can we use it for? Enlighten me. A point that is not moving. For what? something. Anybody?
Parallel axis theorem on it? Like
Okay, I can do that, but what's the point here? Indeed. I'm going to give you a hug one day before the course is over. Please pay attention, guys. This point is not moving. What does that mean? This means that this point, usually, if you have an object spinning about its axis, center of mass axis, that point, the center of mass does not move. Okay. In this case, it moves. So we have to account for the motion of the center of mass and rotation on top of that. However, in the presentation or representation whereby this rolling motion is considered, because this point is not moving, I can go and look at this disk or cylinder or whatever it is and say that this object, its motion can be summarized as a sequence of, I look at this as, because it's not moving, I look at it as a pivot, a center of rotation. Please pay attention here. I can say that the whole motion can be summarized as a rotation of this object about this point that is temporarily not moving. That is momentarily not moving. This point is momentarily not moving. It can be thought of as a center of rotation. So whenever that point is there, whatever point is there, for that brief moment that is there, the motion can be considered to be a rotation about that center. So now your rolling motion can be thought of as a rotation about the center. Whenever a new point comes down here, it becomes a center for new rotations. Right? So in the first approach, we have a combo. Translating center of mass, superimposed on that is a rotation about the center of mass. In the second approach, the speed of this point is 0. There is no translation involved. All the motion can be summarized as, the whole motion can be summarized as a rotation or a series of successive rotations about the point on the wheel in touch with the ground, point B. So I will refer to this point as point B. Okay, you could think of it that way, dot, 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 dot. Okay, it's continuous, but you could think of it as a series of successive rotations about. Why are we able to do that? Simply because for that brief moment, that point has a speed of 0. Let's see if that works. Okay, let me now consider, that is approach A, I will call it. This is approach A, whereby we have translation of center of mass plus rotation about center of mass. Okay, that is approach A. In approach B, I am going to think of this motion as a rotation about that pivot at B, about point B. Okay? So in this approach, guys, we say then, because it's a rotation, or it's a series of rotations, sum of the torques about point B equals to I about point B alpha. So let's examine what forces over there. We said sum of the torques about Cm, center of mass. Now we're taking the torques about the point B. What exerts torques about point B? Point B is the point on the wheel in touch with the ground, bottom of the wheel. That's B right there. What forces exert torques about it? What is a torque? Torque is the ability of a force to generate rotations. We just demonstrated to somebody here that, a force, if this is the pivot, a force here will not cause rotations. A force out will also not cause rotations. Give me a minute. Thank you. Does N create torque about B? Because the point's right in the pivot. Fs is right in the pivot. Mg cos theta points right to the pivot. They all, this is the pivot, they all go into the pivot. Their moment arm, or the perpendicular distance between them and the pivot, is 0. Therefore, these forces will not generate rotations about point B. The only force that acts at a distance, at a perpendicular distance from point B, is what? Not this, not that, not that one. Mg sine theta. So let's do that. See what it will give us. So Samba talks about B. That force is torque of mg sine theta equal to I about B alpha. And what is that, guys? This is the point of rotation B. Where is the force mg sine theta located? A distance r away. Its torque is given by r times mg sine theta equal to, now I about B, please pay attention. What is I about B? The moment of inertia about B times alpha. The ICM of this guy, the ICM was mr squared over 2 because it's a cylinder. What is I about B equal to? I about B by the parallel axis theorem is ICM plus md squared. If you have the moment of inertia of an object about a center of mass axis and you want to find it about a different axis, as long as these axes are parallel, you could use the parallel axis theorem. That's what it says. So ICM is mr squared over 2 plus mr squared, because the distance between the two axes is r. Therefore, r mg, the torque of mg sine theta equals to I about B 3/2 mr squared alpha. Okay, guys. In that approach, we had 3 equations of motion and we had 3 unknowns, F, A, and alpha. In this approach, we're using only 1 equation and we're getting our answer right away. This is the power of using the momentary pivot approach, the approach of using the point at the bottom of the wheel as a pivot of rotation. That's why it's so powerful. Let's divide by R. What will that give me? R here gone, R gone. And what is R alpha equal to? ACM. So now this becomes mg sine theta. It's there. We got the answer. The masses cancel. And really, as opposed to 3 equations in one shot, we concluded that A is equal to 2/3 of g sine theta. Okay? Now, what you could do is, if you want the force of friction, you could go back and still use that equation here. That's fine, and conclude the same result. So, whether you consider rolling to be a combo of translation and rotation about center of mass, or rotation about the momentary pivot, it gives you the same result. Yes?
Does that only work if it's like of uniform shape? Because like if you...
No, let's see, yeah.
If it wasn't like a circle, then point B would be...
Yeah, it wouldn't work. It has to be uniform. Next, guys, we are going to use energy considerations to find the speed of this object. We have done this before for a block or box or whatever mass slides downhill to find the speed at the bottom. And the speed was given by, if you remember, v squared equals to 2gh. Okay? Now we're going to take into account the fact that this object rolls as it goes downhill, as it rotates while it translates. So please take a minute now and see if you can come up with the speed at the bottom. Apply energy conservation, conservation of energy, and see where you can take this. Yes?
Are we trying to get the V center of mass when it just finishes downhill?
Yeah, that's right downhill, right down here. It won't change, by the way. This doesn't matter. Once it reaches the bottom, it goes forever. Believe me. The force of friction. There is friction down there, and there is friction on the flat surface. But believe it or not, for an object rolling freely on a table, if the object is not deformable, and the table is not deformable, and everything is smooth, you could do that to it, and in principle catch it a few days later and on the earth. It will not lose any of its energy. Because I said so. The force of friction is necessary to start rolling motion. Once rolling motion is set on a flat surface, the force of friction becomes zero. Oh my God. Well, think of it this way. You're driving your car on the 401. If you want to accelerate, what do? Hit the gas pedal. What will that do to the wheel, the drive wheel? The wheel, drive, whatever. It will kick it to the ground and push you forward, right? So the force basically from the ground on you will be forward. You hit the brakes, you have an object rolling, you hit the brakes on it, it will seize, it will push the ground, such that ground will push it back. If you do neither nor, what happens?
For the same principle, why there's no velocity at that single point when it's rotating, right? So while it's rotating and there's no velocity at that single point at the bottom.
Different.
Then there's no friction acting in the road.
No, because that force of friction going downhill, the question was, how does that relate to the stuff on a hill, let's say, right? Well, there is a force of friction there, and that's what causes it to accelerate, kind of rotationally. Which?
We're talking about something that's just moving at a constant velocity.
That's right.
It's not being driven forward, it's not being accelerated.
Yeah,
by the friction.
but it's not because the speed of the point is zero. Okay, guys. Approach A says that rolling motion can be considered to be a combo of two things. So the energy that we had, please pay attention, mgh becomes what? 1/2 mvcm squared, speed of cm plus, superimposed on that motion is the rotation about the center of mass. So the energy goes into what? Actually moving this thing forward and also rotating it. So in this approach, this is equal to 1/2 ICM omega squared. For a sphere, guys, so that really is an equal sign. For a sphere, what is the moment of inertia? ICM. Plus 1/2 times 2/5 m r squared omega squared. What is this quantity here? R omega r squared. What is this guy? VCM squared. So, okay. So from this, we get that 1/2 mvcm r squared plus 1/5 mvcm r squared, and that is divided by 10, 7/10 mvcm r squared equal to, that is the total kinetic energy of the object, must be equal to the gravitational potential energy that we lost to get down there. The masses cancel, and v squared cm is what? 7/10⁷ of gh. What was it for an object that did not roll, that just slid? V squared was what? 2gh. What will it be for a ring? Ring has higher moment of inertia. It'll be less than that. It'll be actually, what will it be? I don't know. GH. Just GH. Yes?
You say again initially why it's 1.5 mv squared and not just the I omega squared on its own?
Because we have this, okay, imagine now. You're sitting, the question was, why do we have to have both? Okay, come down here. I got this ball of whatever, from steel ball. It's spinning, right? And I'm gonna bring it in, boom, hit you with it, right? You're gonna feel the energy from the spin, okay? So there's energy in there, right? Now, so there's energy in the spinning. Without it spinning now, I go and throw it at you.
Right.
There is energy in that, there is energy in both.
Okay,
so the object has both. So now when it comes in to hit you, right? It's not just there is, it stops there, but continues to spin, right? So let's say there is no friction there between you and the object. Okay. The object comes in, hits you, it stops moving, but there's still the energy of rotation. Yeah. So we have two modes of energy to consider. Okay?
Yeah.
Cool.
Good.
Okay, this was approach A. Guys, approach B is following the same arguments as B there. Please do it on your own right now. In approach B, we say that the entire motion is simply a rotation about the point at B. Please pay attention. This point has no linear speed. No need for translation of kinetic energy. The motion is considered to be entirely rotation about B. Is that going to work? Let's see. mgh then is equal to 1/2 I about B omega squared. Right? Question you guys did not ask. Please pay attention there. You did not ask the question as to why is it okay to say that we have alpha in rotating about the center of mass in one view of rolling motion as a combo of translation and rotation. We considered alpha to be the angular acceleration about the center of mass. In approach B, we thought of rolling motion as a rotation about the momentary pivot at B, okay? But we use the same what? Alpha. Why should it be the same alpha? You can prove it on your own. You have to prove why should it be the same alpha. I'm going to leave it with you, okay, to think about why it has to be the same alpha. It's not just because we like it to be that way. It has to be, and there is a way for you to prove it easily. I think I've done it for you in the text. I'm not sure. But you can prove it. So anyhow, what I'm trying to say is that, guys, you can also prove that if you use approach A, you get omega. If you use approach B, it's the same omega. You can prove it. I'm not going to prove it for you. You can think about it. Now, mgh then equals to 1/2. What is I about B? We did that just a second ago. 3/2 mr squared omega squared. Okay? What is that number? That guy is VCM all squared. So please pay attention. It says that mgh equals to, oh no, hold on. I apologize. I was thinking this, so erase all that, please. I about B. This is point B. I about B for the sphere is what? ICM plus md squared. Okay, let's, where is d? D is the distance from here to there. D is r. So that is ICM for a sphere is 2/5 m r squared plus mr squared. That turns out to be, I don't know what that is. 7/5 m r squared. You plug it in there, you get the mgh equals to 1/2 into 7/5 m r squared omega squared. This is the same as VCM, and you end up with VCM squared equals to 10/7 GH. Okay? So whichever approach you use is fine. By the way, we're stopping here.